This is question 3 from the tutorial sheet on the triangle of forces questions. So in this question, we've been given information on a weight that has got a hook attached to it and one rope there, and another rope pulling out to the right as well. And we're given information about the direction of all these forces, but only the size of one of them. If we're to compare this to question 2 in the same tutorial sheet, we actually have a bit more information than question 2, because we know not just which angle of direction the force in, but which way they're pointing along the line. So for example, the pulling rope's pointing to the right or the right. We're not left in any doubt about if it's pulling left or right. And the hook is pulling the rope up into the left there. So this makes it in some ways a slightly easier diagram to draw than we did in question 2. But we'll follow all the same procedures and take care to assemble the diagram correctly, and we'll reach the correct answer by doing so. So as before with all of these questions, we'll start off by establishing a scale for the diagram. This is essential for us to be able to use our diagram to measure the other forces. So I've commented in other videos about what sort of sensible scales you may want to pick. Here I'm picking a scale of 1 centimetre and I'll mark that in here. There's no need, I should say, to mark it your 1 centimetre like this. I think it's helpful for the video though, because I'm not using a proper ruler here. I'm going to say 1 centimetre is equal to 200 newtons. Now, this is quite a small scale, and if you've got room in your paper, you might want to try and do 1 centimetre equal to 100 newtons to give you a more accurate diagram. But knowing the scale of the whiteboard, it's better that I choose this. And we know we need to draw in all of our forces to scale. But we only know how long one of them is going to be, and that's a downward force due to the weight. That's a 2000 Newton force acting directly down the way. So we know on our scale that makes it a 10 centimetre line. So that's what we're going to draw in here. So that's our 2000 Newton force acting down the way. And as in every other question, we want to make up a triangle, and each of the forces the different side of the triangle. And what we can do is that we can join these all together in order. But what we don't know is where the 30-degree hook rope and the right pointing pulling rope meet. So we have to join each of these to a different end of the vector we do know, and that allows us to put it all together. So let's do that. So we can just really think about moving my paper. And this is obviously the advantage of doing this on the whiteboard, is I can move my question about here. And again, another good advantage of doing things in pencil, first of all, when you're drawing them. We're going to start off by drawing the rope and the hook. And we know that's an angle of 30 degrees away from the vertical direction. Now I've got to, it says 60 in my ruler because that's the angle from the horizontal, but this is going to be an angle of 30 degrees up from away from the vertical here. So I'm going to, I'll again colour code this. I'll use blue for this line here. So this is the rope that's connected to the hook, and it's going to go up some distance in this direction. We know it's acting up the way because there's an arrow on it in the diagram. We don't know how far it goes yet. So just to make it all clear what I'm doing here, I'll mark this in blue on the diagram. And just to show you where these angles are coming from. If it's 30 degrees from the wall, or the vertical is 60 degrees here. So what my ruler was showing was this angle here, 60. But of course, that means that's 30 there. So we know that it has to head off up to the right from that. And we know the other vector needs to arrive at, I'll mark it here, it needs to arrive at this point coming from the left to the right. So I can actually draw this vector backwards and bring it out to meet the blue vector. I'll mark this one in red so that we can see where it is. So it's going to be arriving at this point here. This is going to be the end of our journey. So we just extend it back to see where it meets the blue line, and this is where they meet here. So I can stop the line there. I'll just call this in red on the diagram as well, just so it's absolutely clear what vector I'm referring to. I can rub out the X a little bit because we don't extend them beyond where they meet. And of course, we already knew that was pointing to the right because it shows us in the diagram. I'll mark that in as well. So having drawn in our diagram, we just need to measure these two lines and convert them into newtons using our scale. Now this will be a bit rough in mine because I've used quite a small scale, but we've got 1, 2, 3, 4, 5.5. I'd say it's 5 3/4. We'll call it 5.7 because we'll take it to these millimeters. We'll say it's 5.7 centimeters. And 5.7 times 200 will be 1,140. I'll just check that. Yes, it is 1,140 newtons, and we'll measure the blue line as well. Now, as I've said in the other videos, if you get an answer different than mine, as long as it's somewhere close to it, your answer could be more accurate than mine, but mine should be roughly in the right region. It won't be perfect, but it won't also be completely out either. This is 2, 4, 6, 8, 10, 11. It's 11.5 centimeters. And again, you might get something a little bit different from that, but in the same region. 11.5 centimeters, and that is going to be 2,300. And we would expect that this blue line is going to be longer than the black line we drew. We've actually drawn a right angled triangle here, and if we wanted to, we could actually check that these made sense using Pythagoras' theorem, but we're not required to do that, so we won't. So that's how we would solve this question. So slightly different to question 2. In some ways, slightly easier because we know which way the forces are pointing to begin with. But we've been able to identify the two unknown forces by drawing our scale diagram and then measuring off once we found out where they met. And that's how we would answer question 3.